results pretty instantaneously, so that's the benefit of that. So we're going to back up a little bit. We talked about rocks and minerals last class. This class, we're going to return to the sort of intro to the Earth, intro to disasters, and then on Wednesday and Friday, we'll talk about plate tectonics, and we'll talk about continental drift. So we looked at tsunami last before Earth materials, and I wanted to use tsunami as a sort of case study of the things that we can do to try to prevent death, damage, destruction as a result of disaster. And there are really kind of three big things we can do. So the first thing that we can do to mitigate or lessen the hazard with regards to disasters, and specifically in this case with tsunami can be extremely devastating, is we can monitor them. If there's an earthquake in the ocean, as we'll see, specialist monitoring stations like the Pacific Tsunami Warning Center, which is pictured here, can monitor the ocean surface using satellites. They can use radars and buoys, and then they can measure the water, the speed of the wave, and figure out what's going on with regards to this tsunami. So this is very, very technology intensive. And with regards to, say, the Sumatra tsunami that happened, and that we'll talk about, the Boxing Day tsunami, monitoring stations need to be constantly staffed, and we need to be sure that they're working. And it's been kind of a failure in this region of the world. After the Sumatra tsunami, there were a lot of stations that were put up. A lot of money went to tsunami monitoring. And now, again, this benefit that we have of looking back at what we did, a lot of these stations are broken, they're unstaffed, and so the warning situation, certainly that's not the case in the Pacific Tsunami Warning Center, but the warning stations, which are very technology intensive, are just being kind of abandoned or not used well. Some areas, Hawaii for example, have building restrictions. And these building restrictions are put in place in hazard-prone regions. We'll talk about this a lot with regards to flooding as well. For example, in 1946, Hilo was hit by a tsunami, and then again it was hit in 1960, and it destroyed the harbor region, a large part of the town. You can see that in the top photo there. Now this region of the city, by land use planning, has a ban on construction of new buildings there, and the majority of the land has been turned into a park. So that's the bottom photo. So you can imagine that if you have a thriving metropolis right in a port and you have a tsunami hit it, you're going to kill a lot of people and do a lot of destruction. If there's a park, then it's recoverable and there's not the death and destruction. So we can use land use planning with regards to building restrictions. Seawalls also, we'll talk about those when we talk about the Tohoku tsunami. Seawalls have been constructed on many beaches, not only for protection against tsunamis, but also the hazards of large storm waves that we'll look at when we look at hurricanes. So the seawalls are designed to make the wave break early, taking the energy out of the wave. So the waves are less energetic before they reach the shore. Some walls are built up actually on the shoreline, and they prevent waves from overtopping the shore and flowing into residential areas. So we'll look at this in different ways and figure out which is better and does this work. Now you have a concrete structure. It's a little more foolproof in terms of the technology. However, you do have to maintain them and make sure that they work. We'll see that with Katrina. The third thing that we can do with regards to protecting from tsunami and all the disasters is education. And these are really three different schools of thought. People have strong pedagogical ideas of what we should do. And especially given the fact that these tsunami warning centers are largely understaffed and largely not working, there's a kind of paradigm shift for people thinking that the best way to lower the death toll is to educate people. It's kind of amazing to think that some people that live in these tsunami-prone areas, the situation is such that they don't know what to look for. People have this misperception that when a tsunami comes, the water's fine, and then there's a huge wave. That's not what happens. What happens is slowly over the course of several hours, and this is dependent on how the tsunami manifests itself, the water slowly retreats. And people actually think that, oh, this is a low tide. And so people start walking out on the seafloor, collecting rocks, looking at things, so they're way out in the harbor when the first wave hits. So it has been shown in many cases that if you educate people using pamphlets, using cartoon diagrams so that you don't have to translate it into Khmer, into all these different languages, If you educate people, if you feel the ground shake, get to high ground. If you see the water retreat, get to high ground. That's a lot better at protecting people. You're not obviously protecting the buildings, but protecting people from the damaging effects of tsunami. So then looking at tropical cyclones, they're a major natural hazard, can cause large numbers of fatalities and damages. And we're going to look a lot at these. Sorry, I see that my battery is dying. We're going to look a lot at these. And from an energy point of view, this is quite extraordinary. These are monster storms. The statistic that I like to tell people, or the fact that I like to tell people, is that a Category 5 hurricane has 200 times the global capacity of we humans to generate electricity. So if we turned on all of our generators all around the world to full power, corral them into a relatively small area, again relative to the whole Earth, we would have to multiply that by 200 to get the power, the energy, in a Category 5 hurricane. So these are monster storms, and I'll show you some pictures of what happened. Flooding, flying debris, etc. So these are huge storms. This one is the Cyclone Gorky, which was in Bangladesh. It killed 138,000 people and left 10 million people homeless. So these are big storms. They devastate large areas. So for example, Hurricane Katrina, which is in 2005, there were gale force winds that were over 120 miles per hour, and they were extending from the storm center, and they're radial or circular, so that's about 240 miles wide from one side to the other of these winds. So huge amounts of wind, torrential rainfall, widespread flooding for several weeks potentially. And in Hurricane Floyd, there were floods in the river basins over which Hurricane Floyd passed that exceeded the 500-year storm event, flooding storm event. We'll look at recurrence intervals in this class as well. So a storm so big it happens once every 500 years, and this was happening all over the place. So there were about $6 billion worth of damage done with that. This is another picture of the quantification of disasters. We looked at the moment magnitude scale, and we looked at earthquakes briefly. This is a different scale. This is a cyclone scale. They're divided into categories depending on the strength of the wind, and then also the storm surge. And you may or may not be acquainted with this scale called the Saffir-Simpson scale. And they're intended primarily for measuring the potential damage and the flooding that it will cause upon landfall. So what you can see, there are 5 categories. And again, you don't have to memorize this all, but understand that it's based on the wind speed. It's also based on the storm surge height. And then you can back into how much damage will we expect. So this is a situation where we can start to figure out how far away should we evacuate and what sorts of damage is going to happen, what sort of rescue and relief efforts are needed. So that's, again, with this scale. And it's as with the last disaster we looked at, the more powerful things are, the less frequently they happen. So Hurricane Katrina, we'll talk about that, and you have a case study in your book, one of the costliest, one of the deadliest hurricanes in the history of the US. It was the 6th strongest Atlantic hurricane ever recorded, and the 3rd strongest hurricane on record that ever made landfall in the United States. So we'll look at a lot of things about this. And this is a radar image of Hurricane Katrina coming in, making landfall in Louisiana. The bottom is a storm track to show where it happened. There were almost 2,000 people that died, which is unheard of in a developed country. And the damage was $81.2 billion. So we'll look at a multitude of factors that made for this to be very damaging, both from a land use planning, New Orleans being below sea level, from a emergency response point of view, as well as simply the atmospheric phenomena. What happened, how it fell, how it made landfall, how the levees should have been strengthened, but they weren't, how the gates were left open and they shouldn't have been, how people thought it wasn't going to be so bad and didn't evacuate. Why? Start talking about level of confidence of these predictive things. So we will look at Hurricane Katrina, and those are big storms. There's some more pictures of the damage from Hurricane Katrina, a flooded roadway, and then some of the flooded surroundings in New Orleans, bridge damage, bridge collapse. So New Orleans you can think of kind of like a bathtub, in that It is below sea level. It's on a subsiding delta or the mouth of a river. And it used to be that when there was no flood control mechanism, when the river flooded, it would dump sediment out. So it would keep that land area above sea level. Now we have all of these flood control mechanisms, so we don't let the area flood. We pump, we have dams, we have levees, we have every flood control mechanism you can possibly imagine to keep New Orleans above sea level. The problem with that is when these things fail, either due to operator error or due to catastrophic storms, then you have bad situations. I don't know if you remember watching the water just pouring in from the broken levees that had been overtopped and had failed, and they had to fix the levees before they could pump the water back out. But imagine trying to fix a levee, a big, huge concrete or earthen, depending on where you are, embankment, while the entire ocean is pouring in over it. They're putting down sandbags, and you just watch the sandbags dump away. So New Orleans is interesting in and of itself from the point of view of flooding on the Mississippi River, but also these hurricanes. And many people think this is going to be a test case for the whole eastern seaboard. In the face of climate change, the face of sea level rising, the cities all up and down the Atlantic coast, if we don't do anything to strengthen our flood control mechanisms, then you're going to have flooding. You're going to have these cities dipping below sea level. I'll show you when we talk about climate change, a map of the future if we do nothing. In 100 years, all of Florida is anticipated to be under seawater. It's just going to be gone. So we can use the lessons from Hurricane Katrina in the broader context of the United States as well as Bangladesh and other areas. So tropical storms produce a huge amount of damage. You have some things that we'll talk about, including the storm surge. Storm surge is caused by strong winds that push on the ocean surface. It causes the water to pile up higher than the ordinary sea level. They're particularly damaging, as you might imagine, when they occur at a time where there's naturally a high tide. And that increases the risk of massive flooding fairly far inland. They're extremely destructive to property. They can cause lots and lots of coastal erosion, lots and lots of flooding. And storm surges actually account for 90% of all the fatalities associated with cyclones. So what's happening, the hurricane's making landfall, pushing the water ahead of it. If you have high tide already, then you have a storm surge, then you are in trouble. Massive flooding, very, very far inland. So a couple pictures of storm surge. There's also wind. Remember that a hurricane, a cyclone, I'm using those interchangeably, we'll see why later, is responsible or created by large amounts of wind. And destruction from strong winds will affect a wider region than even the storm surge. It can uproot trees, it can bring down power lines, can damage properties. And so I'll show you a picture of a piece of corrugate. Oh no, there's a, let's see, here, yeah. This is a piece of plywood that went directly through a tree. Enough wind to cause that piece of plywood to go right through the tree. So winds carry building material fast enough to split tree trunks in two, for example. So with these, how do we mitigate the hazard from, or the risk from a cyclone that's happening with such a huge amount of energy, so many bad things, and over such a large area? The answer to this, many people feel, lies in early warning systems that are needed to give people enough time to make their homes safe, whether it's boarding up the windows and doors or evacuating to a designated shelter. So this can come in the forms of alarms, sirens, something sounded throughout the town, or notification by radio, television, cell phone warnings, local enforcement services coming around. So in these cyclone-prone regions, infrastructure can be in place to decrease the damage from the cyclone. So we want to monitor, we want to put infrastructure in case, and then for all of these other pieces to work, we need to educate the population about the threat of the storms and what to do in case of emergency and get them to listen. A lot of the deaths in New Orleans came from the fact that people were lulled into a false sense of security. The warning systems and the sort of predictive methods weren't what they should have been back through time, and so we issued probably too many warnings. Get out of New Orleans, it's going to flood. Get out of New Orleans, there's going to be a hurricane. And then people left, and that's a huge inconvenience, right? And then the storm amounted to nothing. Every time you do that, you erode the confidence of the general public, so next time they're less likely to go. until we got to a point with Hurricane Katrina. Again, I don't know if you remember seeing this, people on TV from the mayor to the president and everyone in between saying, get out of there, this is a huge storm. And then people sitting on their front porch with their drinks, laughing, waiting to weather the storm. And surfers out there on the big waves. So every time you put an evacuation measure in place that turns out to nothing, you're going to get more people staying behind, which then will increase the death toll. So monitoring is important, but educating people about how to deal with this is incredibly, incredibly important in places that are prone to these different disasters. So the bottom line before we move to sort of introduction to Earth, these hazards, such as earthquakes, tsunamis, cyclones, volcanic eruptions, etc., they're a major cause of fatalities. This graph shows the number of deaths per year due to natural hazards. Remember that this is in addition to natural global fatalities. So these are just natural disasters. Every year there's 10,000 fatalities, right? But this is a log scale. So with the big event, the number can rise to tens of thousands, hundreds of thousands in the big, big event. They can't be stopped. So what we can do is to implement measures to lessen the impact they have on the population, whether it's from early warning, whether it's from evacuation, whether it's from education, whether it's from good building methods. So that is the end of our talking about disasters from a general point of view. We're now going to move into a bit more of an introduction. Again, we have including today, we have 3 more days of introduction. That's the last slide. 3 more days of introduction today and 2 more before we get into actual disasters. So we have a good grounding in disaster science and an introduction. So we're going to start at the beginning here. We're going to look at the origin of the universe. We're going to look at our galaxy. We're going to look at our solar system and then drop down to Earth. This is important because when we start talking about atmospheric phenomena, when we talk about meteorite impacts and that sort of thing, it's very important to have a solid fundamental on the origin of the universe. We'll go through this pretty quick. And then when we get down to Earth itself, these cycles that Earth experiences are another powerful mechanism by which we have disasters. So again, looking at these disasters, we're talking about the fact that Earth in places concentrates some form of energy, whether it's heat, whether it's electricity, whether it is pressure. There's some form of energy that gets concentrated, and these gradients can only build up to so much. Strain on an earthquake boundary, electricity in a cloud, and then they equalize out. And in this class, they equalize out in a very violent, pretty instantaneous manner. So we're looking at the most extreme parts of geology. Right. So we'll look at the beginning. I'm just going to put these all out so then I can talk about them. Yeah, good. Okay. So starting at the sort of beginning, and this being a Jesuit college, I am simply telling you the scientific understanding of what is going on. I'm not trying to challenge your belief system. So please don't pull the God card on me on the quiz, because I'm afraid I'm going to go to hell if I mark you wrong. At your age, I'm not telling you what to believe or not to believe. I'm telling you what science has observed, and it's constantly changing. So starting at the so-called beginning, BA stands for billions of years ago. About 15 billion years ago, it is thought that all matter and energy was at a point. And by point, I mean about 200 miles in diameter. But relative to the size of the known universe now, that is an incredibly small point of infinitesimally high matter and energy concentration. And it blew up, and it's been expanding ever since. Now, a popular misconception about the Big Bang theory is that there was a bang and it's over. That's not the case. If you ever think about seeing an explosion on TV, a car explodes or something like that, it's all bang. We are living inside of an ongoing explosion. This is an explosion that is going on, and we are inside of it. I'll show you where we are relative to the rest of the universe. So again, all matter and energy was at a point, blew up, it's been expanding ever since. The theory that was held for a long time is it's just going to keep expanding forever. It had overcome long ago its gravitational maximum. It's just going to keep on expanding. Things are going to get less and less concentrated, and then, just keep getting bigger and bigger. Recently, and by recently I mean the last 25, 30 years, astronomers, astrophysicists, other people have discovered a lot of matter in the universe that we didn't heretofore think existed. It didn't emit light, black holes, and then also dark stars, quarks, all sorts of things that are beyond the scope of this class. The point is that there's a lot of matter here that we didn't realize existed. And so it may be that we have not, in fact, surpassed our gravitational maximum. The significance of that is that maybe that the universe gets to a point where gravity causes it to stop expanding, like stretching a rubber band, and then it starts to shrink back onto itself. Geologists affectionately refer to this as the big crunch. So it may be that we come to a point, this maximum, and come back down, crunch back down onto ourselves to that same point, and then expand again. I read an article maybe 3 years ago in Physics Today that said, it's very difficult to understand, mostly math, but it said that not only is this going to happen, but it's happened 6 or 7 times in the past. There's been this yo-yoing of an explosion that comes back down onto itself. Obviously a very poorly understood phenomenon, but this is the scientific explanation of what has happened. We know that the universe is expanding because something called red shift is going on. Red shift is when you look at stars, distant stars, through a telescope, the light that's emanating from those stars is shifted towards the red end of the spectrum, the electromagnetic spectrum, visible light. Maybe you don't have an intuitive feel for that, but it is very similar to what happens with sound. And if you're standing on Commonwealth Ave and a motorcycle is far off in the distance and it's coming towards you, what do you hear? Yeah, so the pitch, so if it is absolutely high and fast. If you're standing here and it's coming towards you, you hear it sounding low and then come up to high and fast, right? So it'll go when it gets to you. And then what does it sound like when it's going away from you? Right? If you're on the back of that motorcycle, if you're driving that motorcycle, is that what you hear? Do you hear this cyclical thing? No, you hear the same the whole time, right? So sound is shifted by the Doppler effect as something is coming towards you and then as it's going away from you. So the going away Doppler effect analogy is red shift. We will know that the universe is starting to contract onto itself when light from distant stars, instead of shifting towards the red end of the spectrum, will be shifted towards the blue end of the spectrum. We know, okay, it's starting to contract again. How worried should we be about this? Should we be worried? Oh gosh, the universe is going to collapse? Yeah, we shouldn't be worried at all, exactly. It's been 15 billion years and it's still expanding. So, worst case scenario, it's going to be 20 billion years if it starts going back 5 billion years from now to a big crunch. Nothing we need to worry about. But this is what the current understanding of the whole universe is. And we've recently photographed the edge of the universe. Quite spectacular that we're able to do that. Again, put these all out. Okay. So dropping down a level to the galaxy. There are many known galaxies in the universe. Again, this is not a class on cosmos, so we won't talk about them. But we are in a galaxy called the Milky Way galaxy. The Milky Way galaxy consists of between 200 billion and 400 billion stars. Unfathomable amount of stars. And most of them are in this central bulge. So I've tipped this up in this cartoon diagram. If you looked at it flat, you'd see this central bulge where most of the matter and energy are located. And then there are 2 arms, and the arms are slowly rotating. The whole thing is slowly rotating due to conservation of angular momentum. So those multiple arms there are not the case. It's just designed to show movement. So there are 2 arms, flattened disk, slowly rotating around, 100,000 light years across. Again, 200 billion to 400 billion other stars in addition to ours. It's slowly moving around. And I put that you are here because we're about 3/5 of the way out one of the arms as the matter trails off into nothingness, into space. So we're just sort of, in many ways, an insignificant little planet circling around an insignificant little star as the matter from the Milky Way galaxy trails off. If you've ever seen pictures of the Milky Way galaxy, we're able to photograph it even though we're inside of it because we're at the sort of edge of it. We can look into it that way. So that is the galaxy dropping down a level. Dropping down one more level, we'll look at the origin of our current solar system. And we do this again. I will talk about this stuff when we talk about meteorite impacts. So conceptually, this isn't a picture of it, we used to be a first-generation star and solar system. Pretty boring, probably mostly hydrogen and helium is the thinking. The sun at the center of our first-generation solar system burned out and exploded and engulfed the other planets, or the planets of it, and caused something called a nebular cloud to be formed, which is just a big accumulation of dust and gases. Gravity, something that we'll look at either the end of today or on Wednesday, gravity, the force of attraction between two particles, caused two things to happen. Caused the dust to start to accrete together, to slam together. Two particles of dust exerted gravity on each other and came together. And then two more and came together. So this planetary accretion is what it's called, caused the cloud of dust and gases to start having larger chunks in it. The sun, as well as the planets that are orbiting around the sun, Earth, for example, used to be the size of a speck of dust. And then dust kept accumulating onto it, larger and larger impacts, caused the Earth to grow to the size of a golf ball, and then a baseball, and a softball, and a basketball, going bigger and bigger until it became the size that it is today. So that's planetary accretion. All of the planets became larger and larger with the sun in the center. And so that's what this picture is. The first generation star burned out, exploded, and then the accretion, the condensation of the material caused it to start to flatten and spin. Again, I always struggle with how far to go into this in a non-science class about conservation of angular momentum, this rate of spin. But so it caused it to flatten and start spinning in one plane. So going from A down to here, these are called planetesimals or protoplanets. Planets are starting to get larger and larger. Asteroids are hitting them, growing bigger and bigger. At the same time as the rocks were getting together, essentially, the nuclear reactions were happening that caused just simple hydrogen and helium and simple elements to fuse together, the process of nuclear fusion, to make the more exciting elements in our solar system. All the naturally occurring elements in the periodic table happened during this transition from a first to second generation star. Atoms slamming together, making the fascinating stuff that's on Earth that we'll talk about for the rest of the semester, and the other planets. So we have these planetesimals, the end of A goes up to the beginning of B, the spinning, flattening, and growing the planets to the size they are today. So we are now orbiting around a second generation star. So then we get to where we are now, really, our solar system. And we already talked about all of this. The second generation star. We have how many planets? How many planets? 8, right? We kicked Pluto out. Why did we kick Pluto out? Dwarf planet, right? So Pluto, it has a weird orbit, but also in order for something to be classified as a planet, it has to, they call it clear its own neighborhood. It has to be big enough and exert enough gravity so that any rocks, any sort of debris in its area will accrete onto it. That didn't happen. News for maybe some of you, maybe not. We should have 9 planets, and I'm not talking about Pluto. I'm talking about the fact that on the other side of Mars, there's an asteroid belt. Lots and lots of asteroids. Why am I not quantifying them? Well, it depends on when you cut off the size. If you talk about really, really small, you're talking about trillions of asteroids. Big ones, hundreds of thousands, and they are on the other side of Mars. It was a failed planet. There should be a planet there, but it didn't get its act together in the process of planetary accretion. So we have all these asteroids that are on the other side of Mars. How worried about that should we be? Hundreds of thousands of potentially life-compromising, if not ending, asteroids on the other side of the next planet. Should be concerned? This class on disasters, we're going to talk about them. Anyone concerned? No, why not? What? Oh, but it has happened. It's happened a lot. It's happened a lot. We are overdue, my friend. So yeah, it has happened. It has caused almost game-ending extinctions. But it's a good point, or a good guess. The reason we shouldn't be worried is because they're tracing within our equatorial plane. So the Earth is going around the sun. They're doing the same thing we're doing. They're not coming from above. They're not coming from below like comets are. And unless something knocks them out of their orbit, they're just doing the same thing we do. So they're harmlessly on the other side of Mars. But that should have been a planet. So the first 4 planets, as you may know, this is on the next slide, are the rocky planets, right? The terrestrial planet, Mercury, Venus, Earth, and Mars. Rocky inner planets. And then the outer planets are the Jovian planets, the gas giants, Jupiter, Saturn, Uranus, Neptune. Big accumulations of gas, essentially. So we will look at what happens when a comet, not an asteroid, hits some of the big planets. We'll talk about comet Shoemaker-Levy and what happened with that. So now we drop down to Earth, where we'll stay for most of the rest of the the semester. We'll go back to space for meteorite impacts. In several ways, this is an average terrestrial planet, although obviously from the point of view of life and free water, it's quite a spectacular planet in our solar system. But it's average in several ways. So that's a terrestrial planet, again, where the Jovian planets are the gas giants, the outer part of the solar system. The things that make our planet spectacular and filled with disasters are first that we have free water. Free water just means liquid water. People that study the possibility of extraterrestrial life, they disagree on many things. One thing they all agree on, that is to have extraterrestrial carbon-based life forms, you need to have vast quantities of water. So it is thought that water, liquid water, is quite literally why we are here. You cannot have life unless you have vast quantities of water. Other planets have some to large quantities of water, but it's either in a frozen or in a vaporous phase. There's some evidence that Mars used to have liquid water, drainage patterns, etc. But right now, Earth is the only planet that has these vast quantities of water. It makes us incredibly notable and exceptional. We also have plate tectonics. We're not the only planet, but we have plate tectonics. That's what we're going to be talking about on Wednesday and Friday. Plate tectonics, the fact that inside of Earth is hot. We'll look at that in a minute. Outside of Earth is cool. So the cool stuff's moving inside, and the hot stuff's moving outside. And that makes for terrestrial land masses to be built, which is handy given that we're terrestrial beings. If it weren't for plate tectonics, the things that cause these horrible disasters, earthquakes, tsunami, volcanoes, all of the terrestrial land masses would be reduced to below sea level within a couple 100,000 years. Sounds like a long time to you, but it's nothing given the fact that Earth is 4.6 billion years old. So we need plate tectonics to have terrestrial environments. And then we have the 3 types of rocks that we talked about last time. So I'll kind of go through those briefly. Perhaps not the best titled slide, but this should be titled Planetary Differentiation. So make sure you understand that, and make sure you understand the difference between planetary differentiation, planetary accretion. So accretion was when the meteorites slammed onto Earth, grew it to the size that it is today. That's planetary accretion. Accrete something, stick it onto something. When Earth was first more or less the size that it is today, it was a molten, homogeneous ball. Remember from rocks and minerals, homogeneous. Same thing throughout, and it was liquid. Gravity caused that to happen, right? Gravity got larger and larger on Earth, caused more and more things to slam onto it. Once it grew to this size, gravity wasn't done with it yet. The center of Earth's gravity is in the center of Earth, and so gravity pulls most strongly on the densest materials. So we started looking at rocks and minerals last time. Gravity pulls the most strongly on the metals. So you can think of the center of our Earth, and this is a very rough coarse approximation, we'll fine-tune it later, as a solid metal ball, iron and nickel. It should be liquid because it's so hot, but the crushing weight of the overlying material that gravity's pulling causes such tremendous pressure that it's forced into a solid. So you have this solid metal ball in the inside of Earth. some of the iron and nickels had complexed or turned into these molecules with silica. Silica is much lighter, as we'll see with volcanic material, than the metals. So it made this glassy metallic stuff, silica mixed with iron and nickel, get pulled as well, but pulled less strongly. And so that became the sort of middle part of Earth. Roughly, we're talking about the mantle. People talk about the mantle as being liquid and flowing. It's almost solid. There's nothing liquid about it. But it's just soft enough, just hot enough that it can very slowly flow. So that's the mantle, iron and nickel that has complexed with silica. And then our crust. Obviously, this is a simplification given the rocks and minerals that we looked at. But our crust is essentially a thin silicate, thin glass shell. So you've heard about these, I'm sure, since very early in your education, the core, the mantle, the crust. But there are two other layers that happen in the process of planetary differentiation. Plate tectonics, which was very active in Earth's early history, was causing volcanoes to spew out huge quantities of gas. And this is a part of the layering process. These gases were still held here. They're not going off into space. They have mass. They're being held here by gravity, but they're so light that they're in vaporous phase at Earth's surface temperatures and pressures. So gravity is sorting, differentiate, to tell the difference between two things, right? Gravity is sorting out the heaviest to the lightest in these onion-like concentric layers. So that was the form of our first atmosphere, volcanic outgassing. We'll talk about that in many different places in this class. And I put this picture up because if you could be on the surface of Earth, right, as this was pretty much complete, but before life started being here, if you looked up in the sky on a beautiful day, instead of it being sky blue, it would be blood red. If you looked at the sun, instead of it being yellowish orange, it would be navy blue. That's because of the way these gases scattered light in Earth's early atmosphere. So then this layering became complete when lots of the water, which is heavy, H2O, started to cool. We're about midway through our cooling history on Earth. We're starting to cool from the outside in, rained down to the surface of Earth and became the hydrosphere, hydro water. So it became water mostly in the oceans, but then also rivers, lakes, streams, and groundwater. So liquid water coats the surface of Earth more or less. Then we have this last layer of atmosphere. And there's some, but by no means an all-encompassing list of gases. Now nitrogen is the biggest gas by percentage in our atmosphere. So we have these layers, again, from heaviest to lightest, from most dense to least dense. And that's the last part, that when Earth started cooling, a lot of that liquid water changed from a gas to a liquid. So those are the layers. Make sure you understand the difference between planetary accretion, growing, and planetary differentiation, sorting. So as we said, Earth is common in some ways with regards to the terrestrial land masses, but it's also quite unique. And I have a slide on each one of these, so no need to write them down. We looked at the rock cycle last time. We will look at the tectonic cycles for the next two classes. So then the hydrologic and biogeochemical cycles are also things we will look at in a general point of view from looking at disasters. We looked at rocks again last time. There are three types of rocks. We looked at the types of them. One thing that we didn't say is that these rocks are always changing into the other types of rocks or to a different version of itself because of tectonics and weathering. So you have this igneous material, it comes up, it cools slowly beneath the surface or quickly at the surface. Cooled lava or magma is igneous rock. As soon as it's exposed at the surface, remember it goes through the process of weathering and making sedimentary rocks, but you can squeeze and heat sedimentary rocks, turn them into metamorphic rocks. You can heat metamorphic rocks even more, turn them into liquid, which is not a rock, right? You can melt igneous rocks and make them into a different type of igneous rock. You can rework sedimentary rocks, make them into a different sedimentary rock. We can squeeze or heat a metamorphic rock, turning it into a different metamorphic rock. And I'm not trying to be confusing here. I'm just saying that these three rock types are always turning into the other two or to a different version of itself because of these cycles that are going on the surface of Earth. Tectonic, which we'll see, and then also the hydrologic cycle. 1.36 billion cubic kilometers of water cycling around on the surface of Earth. And it's kind of funny, most of the water is in the ocean. We'll look at percentages later. The smallest reservoirs here, 1/1000th of 1%, is in rivers. And rivers will do tremendous work on Earth and cause tremendous amounts of disasters. And we already talked a little bit about cyclones, right? Hurricanes, typhoons, cyclones. 1/1000th of 1% of the water's in the atmosphere as well. And you talk about these massive, massive monster storms. So you don't have to have a lot of water in these areas in order to do a lot of work, cause a lot of death and destruction. So we'll look at the hydrologic cycle when we look at rivers and flooding, as well as atmospheric natural disasters. Briefly, this sounds like a long, pedantic word, but biogeochemical cycles just means that you're tracking. It's implying there's a sort of bookkeeping that's able to be done. You're tracking an element as it goes from the life to the rocks to the atmosphere. Wherever these elements go, you can track them and sort of make a diagram of what's going on. So these are some of the main biogeochemical cycles on Earth. We're not in this class, in the way that we did in Geoscience 1, concerning ourselves with the phosphorus, nitrogen, or oxygen cycle, but we are really caring about the carbon cycle from a climate change point of view, looking at how we're throwing this cycle off balance by digging up both coal, oil, natural gas, burning it, putting too much of it into the atmosphere, some would say, and volcanic eruptions putting these carbon elements into, or molecules into the atmosphere. So look at the carbon cycle. I'll skip over nitrogen. We won't be dealing with nitrogen or phosphorus, just to know that there are such things. And then the water cycle, which we already looked at. The last cycle here, the tectonic cycle. Again, this is just a real brief overview because we're going to spend 2 days on it. The inside of Earth is very hot. Outside of Earth, relatively speaking, is cold. So the cold stuff's diving inside, the warm stuff is coming out. And so you have this constant cycling that's creating new land masses and is also causing our first 3 natural disasters. The inside of Earth is hot. The reason why is threefold. 3 things that are going on that cause inside of Earth to be hot. First one we already talked about, planetary accretion. Those meteorites streaking through the sky at 650,000 miles per hour, huge amounts of energy, right? Stopping instantly turns into heat energy. So every time something accreted to Earth, it caused heat. That's why Earth was a molten, homogeneous ball. Nothing could stay solid. It was too hot. And then also, in the transition from the first to the second generation solar system, we talked about fusion at the nuclear level. Some of those nuclear fusions made radioactive materials. So inside of Earth, we have radioactive materials that are undergoing alpha or gamma or beta decay, and radioactive decay is heat. So we have this kind of self-sustaining heat mechanism because there are radioactive materials inside Earth. The last part, gravitational energy. Again, the center of gravity is in the center of Earth. It's pulling on this stuff. We're not getting detectably smaller, but we have gotten smaller because gravity is pulling on Earth, and this pulling causes friction, which is heat. So those are the 3 reasons why the inside of Earth is hot. Because asteroids, because of radioactive material, and because gravity is causing friction. So just to end on gravity, Sir Isaac Newton, gravity. You don't have to work with gravitational equations from a quantitative point of view, but it's important that you understand the parts to gravity. Every particle attracts other particles. There's 2 parts to this. That's a proportional sign. Gravity is proportional to the product of the masses that you're looking at. So you just multiply the masses of the 2 objects. That gives you 1 part of gravity. So from a qualitative point of view, the bigger things are, the more gravity they exert on each other. Simple. The second part is that gravity is inversely proportional to the square of the distance between the objects. All that means is that the closer they are, the more gravity. The farther away they are, the less gravity. We'll look at this when we talk about the tides, the pull of the moon, and to a lesser extent the sun, on Earth's water. So the closer, the more gravity. The farther away, the less gravity. And the bigger the objects, the more gravity. When you combine these two equations, and you add in just a constant, the universal gravitational constant is something that you look up in a table, take out of a book. That's gravity. Again, you're not going to have to work with it, but understand it from a qualitative point of view. The bigger things are, the more gravity, and the closer things are, the more gravity. Gravity is amazing because it holds everything together. It holds everything in the universe together. Holds the mountains together, holds everything together, holds you to the earth. But as we'll see, when gravity is being being destructive, like in the case of landslides, like in the case of meteorite